This next section is about solving constant coefficient equations, which is another example of a higher order differential equation that we're going to learn the particular approach to solve. And we're actually going to start out by talking about that approach because it's one of the more straightforward ones that we're going to do in this class. So, our approach to solve constant coefficient equations is as follows. So we're going to be learning the steps to solve any a sub n, y nth variable, a n minus 1, y n minus 1th variable, all the way down through a1 y prime plus a0 y, all of that equal to 0. So it's a homogeneous problem. And we're going to require that a(n) through a0 are constant numbers. That's why it's called the constant coefficient equation, because the a's are the coefficients. And the steps we follow are going to be, first off, we assume a particular solution to the problem. And that solution is y equal to e to mx. So this is another way of solving differential equations. Last section we covered a lot of like manipulate to integrate in a fancy way. This approach is assume the form of the solution and plug it in and see if it works. And we're going to see a few different methods that do that. So after we've assumed that's the solution, we're going to plug y into the ODE and check if it is a solution. And just an important note here is that we're going to need to take the derivatives of y in order to plug it in. So that's going to be like m e to mx for y prime, and you keep going for however many you need for this particular problem. And then once everything's plugged in, you're going to note that you can really easily cancel e to mx out of your equation. That happens every single time for this type of problem. If it doesn't, something went wrong. And after you do that, you're going to be left with what's called an auxiliary equation that we want to solve. And that actually just becomes an algebraic problem. And we're going to be trying to find all possible roots. M of this equation that's going to be equal to 0. And we're going to need to find as many roots as there are derivatives in the problem. And then once you've found all those roots, the general solution is y equal to c1 e to m1x plus c2 e to m2x down through the last cn e to mnx. So finding those roots algebraically is actually finding that fundamental solution set we can use to write down the general solution. Quick note, these aren't the full steps you need to solve every problem in this section. They're going to be special rules for problems where we have repeated or complex roots. And we're going to do that in some later videos, but I just want you, however you need to in your notes, to note that there's different places later that you might need to check for actually writing down this equation. And then please pause and copy this down if you need to while I cough. But as I've been saying as I was writing down these steps, what's cool about this approach is that it takes an ODE and it makes it into an algebraic equation that we need to solve. But since we need to have n parts of a general solution, we're going to need n roots. So you just need to make sure that that equation has n roots for your solution. And that's really the only tricky thing here. We've got time. I'm going to do a real quick example too. Not if I spend all the time we have left trying to move this little green box though. All right, so next up is our example. This is going to be your participation problem. We've got 2y double prime minus 5y prime minus 3y equal to 0, and we want to go ahead and try to find the general solution. So we're going to follow those steps we had, where the first thing we do is assume that y is equal to e to mx. And I'd like to plug it in, but that means that I'm going to need my derivatives, y prime being m e to mx, and y double prime being m times m, so m squared e to mx. Just note that I'm taking derivatives the same way I would if m was a number. Like imagine this was e to 2x. First derivative is 2 e to 2x, next one is 4 e to 2x. I know sometimes having letters can be intimidating. So my ODE is that 0 should be equal to 2 times y double prime. So I'm going to take that, y double prime, and plug it in, minus 5y prime. So I do minus 5, and I plug in my y prime I just found. And then it's minus 3 times y, so I just plug back in that first y e to mx. Sorry. And then the next step is when we note that it's really easy to factor out e to mx. So I've got e to mx in every term right here. So that's going to leave behind 2m squared minus 5m minus 3. And that's still supposed to be equal to 0. And so sort of if I divided out that e to mx, or I note that this needs to be equal to 0, so it's good enough to make that part in the middle equal 0, I end up at my auxiliary equation, which is 2m squared minus 5m minus 3 equal to 0. And if I factor that, I know that I need a 2m there. I know you all do that special like box factoring. I was taught to guess and check. Yep, it's minus 3 and plus 1 because I need lots of minuses to make my minus 5. And you could check that this works, but it matches my notes. So we're good. And in that case, if I want it to be equal to 0, then either of these two things could be equal to 0. So in this case, I would get 3, or in this case, I would get minus a half. To solve that equation, or in the notation of how we wrote out those solutions in the steps. My m1 first root is 3, my m2 the second root is minus a half. And the general solution is taken by multiplying by constants and putting those m's back into the exponential. So e to m1, or 3x, plus c2 e to m2, or minus 1/2 x. I'm just going to write right here so that you know what I'm doing. That's e to m1 and e to m2 from the steps on the previous page that I will flip back to, but I think you might be writing, so I'm giving you a second to pause if that's you. But see over here, we just found those m's in step 4 and then plugged them into e to get our general solution. So that's what I did in that last step, was I found those numbers and I just plugged them in to y. And then that's kind of our first easy example. Next up, we'll move on to thinking about when the roots don't quite work out that nicely.